Please pause the video and try this problem. Now let's discuss. Let's start by numbering the carbons. Now you should know that Me stands for a methyl group. So this Me also includes a carbon, but that carbon is not very easy to number, so I won't number that carbon. Now let's assign roles. We know that a neutral bromine is a good leaving group. That makes carbon 4 into our alpha carbon. And carbon 4 is a secondary alpha carbon because it's attached to 2 carbon chains. Now to identify our nucleophile or base, our electron donor, we look first for a negative formal charge. But none of these atoms has a negative formal charge. This methyl group is covalently bonded to the OH. This molecule consists only of non-metals, so it's a completely covalent compound, and there's no reason to assign it any formal charges. With no formal charges, we can say that this neutral oxygen will be our nucleophile or our base. It wants to donate electrons because of its lone pair. Now we have to choose the mechanism using our table. The secondary alpha carbon puts us in the middle row of the table. Neutral oxygen in an alcohol puts us in the left-hand column of the table. So the table predicts 2 mechanisms, SN1 major and E1 minor. Which of those should we draw? Well, look at the instructions. The problem says draw the product parenthesis S. That means draw the product or products. Well, those types of instructions imply that in this case we should draw both the major and the minor mechanism to get all the products. So it looks like we're going to predict that the mechanism here will be both SN1 and E1. So we should write down those mechanisms. Remember, this handout that contains the table also contains a summary of what happens in SN2, SN1, E2, and E1 mechanisms. So now we're going to have to review what happens in an SN1 mechanism. The first step for an SN1 mechanism is for the leaving group to leave the alpha carbon. Well, we know how to write the electron pushing arrow for that step. Now we draw the product of that step. This arrow tells us to break the bond between carbon 4 and the bromine. Carbon 4 starts neutral and loses electrons, so carbon 4 becomes positive. It's crucial to include this positive sign. The bromine starts neutral and gains electrons, so the bromine becomes negative. Now, in our second step, the nucleophile is going to join the alpha carbons. Let's show the roles for that step. Notice that an SN1 mechanism, so I'm doing SN1 mechanisms right now. Let me remind myself of that by writing SN1 here. Notice that in an SN1 mechanism, we use a nucleophile, not a base. So in this mechanism, the neutral oxygen will act as a nucleophile, not as a base. Well, a nucleophile reacts with an electrophile. So we have to find who will play the role of electrophile. An electrophile is an electron receiver. Well, this positive formal charge will make the carbon want to receive electrons. When there is a positive formal charge on a carbon, a carbocation, that's a good clue for an electrophile. Now you can see why it was so important to get this positive formal charge correct in this picture. Well, now we can draw the electron pushing arrows for this step. A nucleophile donates electrons to join an electrophile. So the electron pushing arrow for a nucleophile and an electrophile looks like this. Here we've shown the neutral oxygen using its lone pair to donate electrons to join the positive carbon. A carbocation has an incomplete octet, so there's room for the nucleophile to join on this carbocation. Notice again, an SN1 mechanism uses a nucleophile in this step, not a base. Now let's draw the product of this step. This arrow tells us to form a bond between the oxygen and carbon 4. This arrow tells us to form a bond between the oxygen and carbon 4, form a sigma bond using this rule. The head of this arrow is on carbon 4, and the tail is on the lone pair on the oxygen. Well, in this picture, carbon 4 is not yet sharing the electrons in the lone pair in this picture. That's the situation when an arrow tells us to form a sigma bond. So here's that new sigma bond between carbon 4 and the oxygen. Now the oxygen is at the beginning of the arrow. The oxygen starts neutral and loses electrons. So the oxygen becomes one step less negative, one step more positive, and the oxygen changes from neutral to positive. Carbon 4 is at the end of the arrow and gains electrons, so it changes from positive to neutral. The most common mistake on this step would be forgetting to change the formal charge at the beginning of the arrow. Forgetting to change the charge on this oxygen to positive. Make sure you got that right. Now, should the oxygen end up on a wedge or a dash or both? Well, you should know that a carbocation has trigonal planar geometry. And a nucleophile can attack something that's planar, flat, from either of two directions. That means the nucleophile will attack both from in front of the page and from behind the page. So we get two products here, one with the oxygen on a wedge and one with the oxygen on a dash. Notice that the mechanism branches into two paths here. Let's erase these labels now, because these applied to the previous step. Now, is this mechanism finished, or do we need another step? You might think that we're finished because you might have learned that SN1 is a two-step mechanism. But it looks like we're not finished because our main product still has a formal charge. Usually the mechanism is finished when the main product has no formal charge. So it looks like we need another step. We need an acid-base cleanup step to clean up this positive formal charge. Our third step is going to be an acid-base cleanup step to clean up this positive formal charge. So we need to assign the acid and base roles, and we look first at the positive formal charge on the oxygen. The positive formal charge on the oxygen makes it want to act as a strong acid. A positive formal charge makes the oxygen want to receive electrons to give up its proton. And we've already seen that a neutral oxygen in an alcohol can act like a weak base. Remember, we do have a Br-, but we've seen that when we have a water or alcohol solvent, we generally prefer to use the water or alcohol solvent as the base, rather than something like Br-, because Br- is such a very weak base. Now, you might be worried that since we already used an alcohol in step 2, does that mean we won't have any alcohol left for step 3? Well, no, because remember again, the alcohol is also the solvent. And the liquid solvent is always present in large excess. So we never have to worry about running out of solvent molecules. We can use the solvent in as many steps as we like. Now let's draw the electron pushing arrows for this acid-base step. Remember that a base donates electrons to take a proton. So the base should go at the beginning of the electron pushing arrows to show that the base is donating electrons. And the hydrogen should go at the end of this electron pushing arrow to show that the base is taking this hydrogen, this proton, from the acid. And then the second arrow points to the oxygen with the positive formal charge to show that the oxygen is receiving electrons from the end of this arrow in order to give up its proton to the base. My experience is that students have a really hard time getting the correct electron pushing arrows for an acid-base step. So double check to make sure that you drew your electron pushing arrows correctly for this step. Now let's use the electron pushing arrows to draw the products from this step. This arrow tells us to form a new bond between the oxygen and the hydrogen. We follow this rule, and I'm now showing that the oxygen is bonded to two hydrogens. The oxygen is at the beginning of the chain of arrows. The oxygen starts neutral and loses electrons, so the oxygen becomes positive. The most common mistake on this step would be forgetting to change the formal charge on the oxygen at the beginning of the chain of arrows. This arrow tells us to break the bond between the oxygen and the hydrogen, which I've already kind of shown here. So now we followed this rule and broken the bond between the oxygen and the hydrogen. The oxygen starts positive and gains electrons, so the oxygen changes to a neutral formal charge. You can see that in this acid-base step, the base really did gain a proton, and the acid really did lose a proton. And you can see this really was a cleanup step. What did we clean up? We cleaned up the positive formal charge on the main molecule. Now it looks like the SN1 mechanism is finished because now our main molecule has no formal charge. The reaction is usually finished when the main product has no formal charge. Notice we can't get rid of all the formal charges. We can't get rid of this formal charge or the formal charge on the bromine, but our main product, so to speak, has no formal charge, and that's a clue that we're probably done with the mechanism. SN2 reactions are an exception to this pattern, but an SN1 reaction usually ends when the main product has no formal charge. So an SN1 mechanism has two main steps, but notice there may also be an acid-base step. In fact, most of the SN1 reactions that you will see on your exams do include an acid-base step. Notice that in this SN1 we had a very common pattern for SN1. A very common pattern for SN1 is that the first step is the leaving group step. The second step is the nucleophile electrophile step, and then the third step is an acid-base cleanup step to clean up the positive formal charge from step 2. This problem gave us a chance to review the stereochemistry for an SN1 mechanism. Notice that the stereochemistry matters for this problem because the alpha carbon is a stereocenter. This alpha carbon is attached to 4 different groups in the product: an oxygen, a hidden hydrogen, a methyl group, and a more complicated carbon chain. So notice that this carbon chain on the left counts as a different group than the methyl group on the right. So these are stereocenters, so the stereochemistry matters. Well, in that case, an SN1 reaction produces some products with inversion of configuration and some products with retention of configuration. We would say this product has retention of configuration because the oxygen is on a wedge, the same place that the leaving group started. And we would say that this product has inversion of configuration because the oxygen is on a dash, an inverted configuration to where the bromine started. We explained that the reason for this SN1 stereochemistry is because the nucleophile is attacking a trigonal planar carbocation. The carbocation is flat, so you can attack from either in front or from behind the page. For a molecule such as this one, we would actually expect a 50-50% mix, 50% retention and 50% inversion of configuration. Make sure you don't confuse SN1 stereochemistry with SN2 stereochemistry, which I've reviewed here. Most problems that involve an E1 mechanism will also require you to work through an SN1 mechanism. So we went through SN1 here, but keep in mind that I discussed SN1 mechanisms in far more detail in the SN1 video series. Now remember that we had predicted that for this problem we would have to draw both SN1 and E1 mechanisms. So now we have to continue with our E1 mechanism. Now it's important to realize that the first step of E1 is the same as the first step of SN1. In the first step of E1, the leaving group leaves the alpha carbon, and in the first step of SN1, the leaving group leaves the alpha carbon. So we don't need to rewrite this first step. We don't need to rewrite this first step. We can reuse the same first step for our E1 mechanism, the same leaving group step. We reuse the same leaving group step that we used for the SN1 mechanism. We reuse that for the E1 mechanism. Remember to always write down the name of the mechanism you're doing. So now I need to write down that now I'm going to be doing an E1 mechanism. So notice that we have the same carbocation intermediate after step 1 of E1 that we had after step 1 of SN1. Both the SN1 and the E1 use the same carbocation intermediate. Now we draw step 2 for E1. Remember that that's going to be this step where the base takes the beta hydrogen and the pi bond forms between alpha and beta carbons. Well, we expect to use this alcohol as our weak base. But notice that there are two beta carbons. Here we have two beta carbons, and those two beta carbons clearly have different connectivity. You can see that because, for example, beta carbon 5 is directly attached to 3 hydrogens, but beta carbon 3 is directly attached to only 1 hydrogen. That's enough to make it plain that these two beta carbons have different connectivity, so we expect them to give us different products. So we're going to have to draw two E1 mechanisms, once using carbon 5 and once using carbon 3. Well, let's start by using carbon 5. Since carbon 5 is giving up the proton, I'll call carbon 5 the strong acid for this step. Now we draw the electron pushing arrows. Here is the electron pushing arrow that shows our base donating electrons to take the proton. And here is our electron pushing arrow that shows that we're going to use these electrons that get freed up to form the pi bond between the alpha and beta carbons. Now we draw the products from this step. This arrow tells us to form a bond between the oxygen and this hydrogen. The oxygen started neutral and lost electrons, so it ends up with a positive formal charge. This arrow tells us to break the bond between carbon 5 and the hydrogen and to form a pi bond between carbon 4 and carbon 5. Carbon 4 started positive and gained electrons, so carbon 4 changes from positive to neutral. Our main product here has no formal charge, so it looks like we're done with this E1 mechanism. But remember, we have to do E1 again now. Now we have to do E1 using the other possible beta carbon. Now for this version of the E1 mechanism, again, we're going to reuse the same first step. Again, the leaving group leaves, and that produces the same carbocation intermediate that we used in all of our previous paths. But now notice that instead of labeling carbon 5 as the beta carbon, now I'm labeling carbon 3 as the beta carbon. So now we need to draw our second step again. So I've drawn the arrows to show the base taking the beta hydrogen and the pi bond forming between alpha and beta carbons. Again, the base donates electrons to take the beta hydrogen. So now carbon 3 is acting as this strong acid because it's carbon 3 that's giving up its proton. Now we draw the products. This arrow shows the oxygen forming a bond to the hydrogen. The oxygen started neutral and lost electrons, so it becomes positive. This arrow shows us breaking the bond between carbon 3 and the hydrogen and forming a pi bond between carbon 3 and carbon 4. Carbon 4 started positive and gained electrons, so carbon 4 changes from positive to neutral. Again, we ended up with a main product that has no formal charge, which indicates that we're done with this path of the mechanism. So here's our complete work for this problem. Now notice that this problem only asked us for the products. It didn't specifically say that we had to draw the mechanism. So you could get full credit on this problem if you just drew the final products. You don't have to draw the mechanism. And because this mechanism is so complicated with so many branches, there's a good chance that you would not want to draw this full mechanism on the exam simply because it would take you too long. Nevertheless, right now, as a beginning OChem student, right now I would strongly encourage you to write out the complete mechanism for this type of problem at least a few more times. Right now, when you see this type of problem, I would encourage you to write out the complete mechanism with all the branches carefully, just as I've modeled here. You don't have to do that forever, but you should do it at least a couple more times. For a few reasons. First of all, that will give you important practice with these mechanisms so that you can draw the mechanisms when they are required on the exam. It'll also give you a better understanding of what you're doing so that you're not just relying on memory. Also, the mechanisms are our tools for getting the right products. So as a beginner, you should be drawing the mechanisms as your tools for getting the right products. Otherwise, again, you're just relying on memory. If you just rely on memory, you're likely to end up getting the wrong answer if the professor changes the problem a little bit so that your memory doesn't automatically give you the right answer. So when you take the exam, you probably would not want to write this full mechanism if it's not required, just because it would take you too long. But I encourage you to write out the full mechanism for this type of problem a few more times, because it's good practice and builds good organic chemistry insight. Notice that we ended up with 4 main products. 1, 2, 3, 4 main products. That might seem like a lot, but that's not very unusual for this type of problem. It's actually quite common for this type of problem that involves both SN1 and E1 to give multiple products. So it's not uncommon to have 4 different products for this type of problem. We got 4 different products because there were 2 different stereoisomer products from the SN1 reaction, one with inversion and one with retention of configuration. And because there were 2 different products from E1, one where we used carbon 5 as the beta carbon and one where we used carbon 3 as the beta carbon. This problem gives us important practice with seeing the similarities and differences between the E1 and SN1 mechanism. Why don't you pause the video and decide for yourself, how are E1 and SN1 similar and different? Well, here's the answer. The similarity is that both E1 and SN1 have the same first step. The first step for both E1 and SN1 is that the leaving group leaves the alpha carbon, forming the carbocation intermediate. So the carbocation intermediate that's used in E1 is the same carbocation intermediate used in SN1. How are they different? They're different because E1 uses a base in its second step, whereas SN1 uses a nucleophile in its second step. So that brings up the important point, how is a nucleophile similar to a base, and how is a nucleophile different from a base, which we can also review here. This is crucial material for your OChem success. Pause the video and try to articulate how is a nucleophile similar to a base, and how is it different? Well, we can see from these definitions. A nucleophile is similar to a base because they both donate electrons. That's how they're similar. This nucleophile donates electrons. This base donates electrons. How are they different? Well, a nucleophile donates electrons to join the other molecule, whereas a base donates electrons to take a proton from the other molecule. This nucleophile is donating electrons to join this other molecule, whereas this base is donating electrons to take a proton from the other molecule. So we can see how a nucleophile is similar to and different from a base from this example. Here was another example of a base donating electrons to take a proton from the other molecule. So in our SN1 reaction, we used a nucleophile in step 2, but then we had to go ahead and actually use a base in our step 3 acid-base cleanup step. An SN1 reaction has a nucleophile electrophile step, but it also oftentimes includes an acid-base step. Remember that the E in E1 and E2 stands for elimination. These are elimination mechanisms because they're eliminating groups without adding groups. We can see here that in our E1 mechanism, we eliminated 2 groups. We eliminated the bromine, the leaving group, and the beta hydrogen. This E1 was an elimination because we eliminated 2 groups, the leaving group and the beta hydrogen, without adding any groups to this molecule. On the other hand, the S in SN1 and SN2 stands for substitution. SN1 is called a substitution mechanism because we're substituting one group into the position formerly occupied by the other group. We're substituting the nucleophile into the position formerly occupied by the leaving group. The N stands for nucleophilic because the thing that is substituting into the position that was formerly occupied by the bromine is a nucleophile. We followed these E1 guidelines. We labeled the alpha carbon, alpha carbon, alpha carbon, and we labeled the beta carbon that we're using. In this path, we labeled carbon 5 as the beta carbon that we were using, and in this path, we labeled carbon 3 as the beta carbon that we were using. We used beta carbons that were attached to at least one hydrogen, And we knew that there would be two different products here because these two beta carbons had different connectivities. And to confirm, it should be apparent to you that this product that we got from using carbon 5 as the beta carbon, it should be obvious that this product is a different product than the one we got from using carbon 3 as the beta carbon. So for full credit, we would need to include both of those alkene products. We followed this checklist when working through this problem. We numbered all of our carbons in all of our pictures, except for the carbon hidden in the methyl group. Make sure your numbers are all consistent with each other. The purpose of numbering is to make sure that you don't accidentally add or drop carbons in your pictures. For example, this answer is wrong. This answer is wrong because I've accidentally added too many carbons. But it's not that easy to see that there's too many carbons if you don't number all your pictures consistently. Number all the carbons in all your pictures consistently to make sure that you're not accidentally adding or dropping carbons or getting the structure of the carbon skeleton wrong. Label which atoms play which roles. Notice that for every step here, I labeled the roles. Electrophile, nucleophile, strong acid, weak base. Leaving group, strong acid, weak base. Label the roles and make sure you know what the clues are that would tell you that the atoms will play those roles. Label the alpha carbon and write down, as we did here, that we have a secondary alpha carbon. Use the table to determine the mechanism and write down the name of the mechanism. Here SN1, here E1. If you don't write down the name of the mechanism, you're liable to forget what mechanism you're writing down and shift accidentally to the wrong mechanism in the middle of the problem. First, draw the electron pushing arrows for a step, and only then draw the products from that step. Don't begin drawing the products for each mechanism step until you've finished drawing the electron pushing arrows for that step. That way you can use the electron pushing arrows as your tool for getting the right products from each step. And usually the reaction is finished when we can see that the main product has no formal charge. We saw that we needed an acid-base cleanup step after step 2 of our SN1 mechanism, because after step 2, our main products still had formal charges. I know it might seem tedious to go through all these habits on each problem, but beginning students make the fewest mistakes and develop their OChem skills the fastest if they try to make these into habits. By the time you take your exam, you might be able to cut corners and skip some of these steps. But right now, as a beginner, when you're practicing, it's good to go through all of these steps as a habit. And in fact, many of these steps would be very helpful for you to continue using even on your exam. Again, if you don't number carbons during your exam, you're very likely to lose credit on problems from accidentally adding or dropping carbons. Remember, we learned that Me stands for a methyl group. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.